Welcome back, juniors. Today we are only going to cover one wave behavior with sound. We're going to cover all the details with it. And that wave behavior is diffraction, which we've already talked about before. So here's a little reminder. Diffraction, by definition, is the fact that waves and wave energy can be sent around corners. Now here's a sketch of what that might mean, and also a reminder of another fact related to it, which is that long wavelengths bend around corners better than or farther than short wavelengths do. What this means is, and you maybe remember from the water waves video, that if I have high frequency waves that are coming towards this barrier, that they won't wrap around as far as these lower frequency waves do. Or if I have short wavelength waves headed towards this barrier, they won't wrap around as far past the edge of this barrier as the long wavelength waves do. You may also recall from the previous water waves video that a single slit or a doorway here acts like a point source of waves. All that this really means is that you can't really tell the difference at some point if this slit is narrow enough. I mean, a finger tapping and producing these circular wavefronts at this location, at the X, or water waves that were straight wavefronts headed towards this slit. They're indistinguishable, and you can treat them the same. That this arrangement of a barrier with a narrow slit in it produces circular wavefronts on the other side of the barrier. Here's what the details of today's lesson are really all about. If we have two openings or two slits in this barrier, two doorways for these straight line wavefronts to try to pass through, we end up with an interference pattern on the other side. So in the diagram, the blue line is meant to represent a crest, and consecutive ones are consecutive crests in these waves that are headed towards this barrier. So the in-between space that's not marked is a trough. I could have done it in pencil or a dotted line, but you really only need to see that the crests line up together over here in particular places. The space between two crests, two successive crests, is one wavelength. And what we've got going on over here is called an interference pattern. In this case, the locations that are marked with a little O, like here and here and here, would have constructive interference. Constructive because they would build to higher amplitudes at those locations, either because a crest meets a crest at that location, like this spot for example, or here, or here, or here, or because a trough means a trough. Two downward portions of the same wave intersecting with each other will create constructive interference that'll be an extra deep hole in the otherwise flat surface of the water. Here, the locations that are marked with an X have destructive interference occurring. Destructive interference would be when a crest meets a trough. So, for example, here, you can see that the crest of this wavefront is at that location at that time, but the trough of the ones from the other source here is at the same place at the same time. And if a crest and a trough that are equal in amplitude meet up with each other, they will cancel each other out. We'll have destructive interference, and the water would be at its equilibrium height at that location. That's true for all of the places marked X in the diagram. What we want to do now is to try to notice and then justify physically the patterns that maybe you started to notice in the previous picture. And so for that, I've made a tougher sketch. This more difficult sketch to make is supposed to be a side view in 3D-ish, although it's on flat paper taken from an angle of a video on my phone in my physics dungeon of a basement, so we'll see. But here is a diagram of along a barrier, several locations. Let me fold this and get it covered up right. Okay. Several locations where types of interference would be experienced. So here is the source called A now, That was the bottom slit on the previous drawing, and here's the top slit called B now. These two openings will have headed toward them, viewed from above in the previous straight lines. Those would now look like crests, and so here's a crest, here's a crest, here's a crest, here's a crest from the opening at B, or from the waves that would now be forming circular wave fronts on the right side of this barrier past these two slits. Those wave fronts will interact with each other, and in this case, at location 1, we would expect to see constructive interference. And the reason is here. And I'll read it with you. At location 1, both A and B wavefronts have traveled 3.5 wavelengths. You can count them. Here's 1, 2, 3.5. And here's 1, 2, 3.5. This means that they are in phase with each other, and you can see that on the diagram because they're in the same location and headed in the same direction. So they will constructively interfere there. So at location 1, these two wavefronts as drawn would have constructive interference exist here. If this was in a giant swimming pool and we had two sources of circular wave patterns, or two plungers in the water at A and at B, if you were sitting along a wall on the other side of the pool at location 1, you would experience giant waves because where you are, constructive interference is occurring. If we look at the details surrounding that point for points 2 through 5, a different story emerges, and I'll go step by step here. So this is a summary of what happens and why at each of the locations. At location 1, the path length difference, which means the distance traveled to get to there from both sources of the waves, or the length of the path to get from A to 1 versus B to 1, is the same. We already said that they both have 3.5 wavelengths between this wall and this wall. Because the path length difference is 0, those two wavefronts will be in phase with each other. They will experience constructive interference. And here, just to keep track, are the distances that that point is from the wall and really from each of the sources. It's 3.5 wavelengths. If instead we analyzed the waves interaction at location 2, we should talk about how we fill in this row of the same information, or the same table. At location 2, which is closer to A than location 1 was, but further from B than location 1 was, it's reasonable to assume that a place like this location at 2 would exist, where the A distance might have been reduced to 3.25 wavelengths, while the B distance would have been increased to 3.75 wavelengths. If that's the case, then at location 2, there's a path length difference, or a difference in the distance from A to 2 versus B to 2 of half a wavelength. If that's the case, then those two wavefronts would be out of phase at location 2. This will result in destructive interference, which would mean that if you were sitting along this wall at 2, dipping your feet into the water, assuming that this was a swimming pool, that you would experience no waves at all at that location. Here's the same carried out for points 3, 4, and 5. You'll notice that 3, being just on the other side of 1 from 2, has the same numbers but flipped as its distances from point A and point B. Because it's those same distances, the path length difference is still half a wavelength, meaning that at that location we would also expect the waves to be out of phase, and the water in front of position 3 along this wall would have no disturbance in it. There wouldn't be any waves at all there. If we continue, there's some place further along this wall where we would experience a path length difference of a full wavelength. Here in the example, we'd say that there must be a place along this wall that is exactly 4 wavelengths away from point A while being only 3 wavelengths away from point B. That position is position 4. If that's the case, the path length difference being 1 wavelength means that the two waves will be completely in phase, which will result in constructive interference and with big waves if we were sitting on the wall at position 4. The last one, position 5, is further down the wall, and this pattern along the wall would continue to be repeated in cycles for these waves being sourced from position A and position B. We would go through cycles of being experiencing waves from those two sources that were in phase and out of phase, where we had constructive and destructive interference in a pattern as we walked along this wall. I'm now going to attempt the shortest and sloppiest possible proof that I can for any of the equations that are in your data booklet. Here goes. This is a top view of the same situation from the last video, where we have water waves that are being sent through these two openings, A and B, through these two doorways. This is a top view where we've labeled the distance between the openings from center to center little d. The distance from wall to wall is L. And over here, along the wall that we were imagining walking across, we've labeled the same 2 points from before, 1 and 4, are those locations where we had constructive interference occurring because of the path length difference being some whole number of wavelengths at 1 and at 4. I will say that these are consecutive locations along this wall where constructive interference is occurring. That is, that there's no other place between 1 and 4 where we have constructive interference that occurs. The distance from the central to the first maximum here, first constructive interference location here away from the center, is called y on this diagram. What we've got is a right triangle, for sure, this large right triangle with a leg L and a hypotenuse that's labeled L star. And its other leg is y. It's the distance from 1 to 4. We also have a small triangle that's a right triangle over here. And what I'm going to do down below is just to make it a little bit bigger, and we'll compare them. When we compare these two triangles, we see that they have an angle in common, another angle in common because they're both right triangles. We know the hypotenuse of this one is d, and we know that this leg of this small triangle is 1 wavelength. And the reason that we know that, again, is because for constructive interference to occur at location 4, it must be 1 full wavelength farther away from doorway A than it is from doorway B. If we accept one assumption to be true, we're going to have a one-step proof in just a moment here. Here's the one assumption. It is this: as long as the distance from wall to wall is much larger than the space between the two openings, the hypotenuse of this big right triangle is approximately the same size as the distance from wall to wall. That should make some sense if you imagine that we took this wall on this tiny sheet of paper and stretched it out across my whole basement. Then I think you would agree that L star was approximately the same size as L. If we make that assumption, then we have two similar triangles where we know a leg and a hypotenuse for both of them. This leg is y. If we have two similar triangles, we can write proportions. And so here is our one-step proof of our equation for diffraction. By similar triangles, lambda over d, leg over hypotenuse, would be equal to y over L, leg over long leg, which is approximately the same size as the hypotenuse. In the data booklet, this equation looks like this. S is a substitute for y. Little l is capital D, and I think from that you can see that the data booklet equation matches identically to our result here. This is the point in class where if I was at school and had all of the materials that I would need, I would show you two sheets that have concentric circles on them and overlap them. One of them is a transparency and the other one was paper. And if you overlap one onto the other, what you get is these diffraction patterns, these series of concentric circles overlapped on each other, producing constructive and destructive interference in different places. I did not bring those transparencies home, so I couldn't show you on video. The best I can do is I made a graph on Desmos that I'll give you the link to that you should play around with and see how Y is affected by changing the wavelength, changing the distance between the two walls, and changing the separation distance of the two slits. Now that you've played around with that a bit, I hope, the best I can do to connect this to sound is to talk about something you may have experienced at a concert, and also to describe in full detail an experiment that I used to do. This is at a school, I guess for me in my career, 2 schools ago. We did an experiment out on the tennis court where we produced diffraction patterns. So this was the premise. We had 2 loudspeakers that played an identical note. They played, for this example, A440, so 440 hertz. A was just held on a keyboard, actually, out on these tennis courts. And the 2 loudspeakers were 15 feet apart. The speed of sound, we're going to assume, was 1,100 feet, which is pretty reasonable. And across the tennis court, which is 36 feet wide, we just had people walk in a line. And what did they hear is really the question here. So here's the diagram. This is another top view. Here's the tennis court, here's the doubles alley and the other doubles alley and the service line. And here is one speaker and the other. They are 15 feet apart. They're both producing 440 hertz A, and this is a top view of people. It's the best I could do. But here's a head and here's some shoulders, and these people would walk along this line that's 36 feet away. And the question is, what did they hear? If you understand how this is connected to what was on the previous videos and what you just played around with on Desmos, if you did your part, then you know what to expect. Some of these people at their current positions in the picture would be experiencing constructive interference. And with sound, that means that the sound would be really loud. Others in line with them, depending on where they are, would experience destructive interference. That would happen if the distance from them to speaker A and speaker B was exactly half a wavelength different for them, or 1.5, or 2.5, or 3 wavelengths difference in their path length to speaker A and speaker B at a given instant. Here it is worked out, and then we'll explain what it means. First off, the wavelength had to be determined of this sound, and we were given that I was playing a note of 440. So the wavelength of that sound ends up being 2.5 feet, which is a nice round number. If we then know the wavelength and we know the separation distance is 15 feet, and we know the distance away that our observers are, or that the wall was in the previous example, is 36 feet, then we can determine Y. Y comes out 6 feet. What that means in this context is every 6 feet, a person who was walking along this line would experience constructive interference, and then destructive interference, and then constructive interference again. And what that means, it sounds like, which there's really no substitute, especially watching this video on your computer for, is that the sound would go from really loud to non-existent to really loud again every 6 feet. Maybe you've experienced something like this walking by sets of speakers at a concert, but if you haven't, there's really no substitute for it. The last thing worth mentioning for this experiment that we carried out all those years ago, when you were just a wee lad or lass, was that it was way more interesting to play a chord. So if you play a chord on a keyboard that was hooked up to these two speakers, you're playing then 3 or more notes that all have their own frequencies. Because they all have their own frequencies, they all have their own wavelengths that are slightly different from each other. And their wavelengths being different will mean that y, the distance that you have to walk to experience the sound dropping out or being really loud, is different for different notes. So what was pretty much magical that happened, at least I would say, we did this experiment 5 times, and probably 3 of the 5 it was just incredible. The thing that's really amazing that happens is that in the center, where you're equidistant from the two speakers, everything is loud. But as you walk, you will hear the A note drop out, but you might still hear pretty loud one of the other notes that's a part of the chord that you're playing if you're just holding a chord on the keyboard. And so what you get, the full experience as you walk along this line, is that you'll hear one tone go loud, quiet, and in a different time interval, you'll hear another tone that's a part of the chord go loud, quiet, and then the third one will go loud, quiet, and there will be some places where the whole thing goes silent. There'll be other places where the whole thing is loud, and there will be still other places where 2 of the 3 are loud or quiet.